So as we've seen so far, as we've increased our model complexity by adding more features, we run into this problem where our model starts to overfit to the data. What we'd like is some mechanism to parametrically balance the desire to fit our training data, which is our best representation of the world or the data that we will see when we deploy our model, with our need to also ensure that when we see new data, we will perform well on that new data, that we won't overfit to the data that we were given during training. Regularization provides such a mechanism. And the big idea here is we're going to add an extra term or an extra objective to our loss to capture our tendency to overfit. And we'll add some parameter that will allow us to dial or to balance that tendency to overfit with our primary initial goal of trying to minimize our loss on the training data. So we can think of this basic formulation of the regularization problem as combining the loss that we defined earlier, our loss objective, which is to minimize our training error, our loss, on our data, y and x, with respect to our choice of model parameters, theta. We're going to add an additional constraint or objective term that's going to penalize models or parameter choices that have a tendency to overfit. So now how could we make this more formal? At this point, our primary mechanism to measure overfitting is cross-validation. One might imagine choosing a additional penalty that incorporates this cross-validation error, the cross-validated estimate of the loss. Unfortunately, we can't optimize our theta parameters with respect to this cross-validation error because cross-validation itself requires minimizing the loss. However, we will rely on cross-validation to determine how we balance our primary objective of minimizing the loss and this additional constraint or objective term we're about to add. So if we can't use cross-validation, what would be another mechanism or metric we could use to capture whether or not our model is likely to overfit to the data? So you may have noticed in our previous notebooks and lectures that as we added more features, in a sense, as we made our models more sophisticated or more complicated, they tended to overfit to the data. So one formulation of this constraint or objective would be to set a constraint on the complexity of our model. And to do this, we introduce this constraint parameter beta, which is our regularization parameter, and it's going to be the knob or dial that we can tune to adjust this trade-off between fitting our data and complexity. And then we can think of this complexity function as a way of regularizing our model or constraining it so that it doesn't overfit to the data. Now we're left with the challenge of how do we define this complexity function? Well, one way to think about this in the context of linear models is that the complexity is really the number of features that we have in our model. And so as we add more features, we're increasing complexity, and we'd like a way to control the number of features we add. So this leads to a basic formulation of complexity, where we say the complexity of a model is the number of non-zero features. That is, as we set a feature to 0, that is equivalent to removing that feature from the model. So we could frame this as a kind of idealized form of regularization, one that we might be able to optimize. Unfortunately, solving this problem is NP hard because it requires a combinatorial search over the number of features. So what we would like is some simple approximation to this objective that we could directly optimize in our loss minimization problem. And so a simple solution to this comes in the form of norm balls. And so I want to talk about these different norms and some of their trade-offs in the optimization problem. And that will give us a collection of regularization functions. So here I have a cartoon illustration of the loss surface for a two-dimensional model. So we have parameters theta 1 and theta 2. And these contours correspond to the contours of the loss surface, with the optimal loss here at the center. So you can imagine this is a squared loss, these are pretty elliptical contours. And this red dot here is the best parameters that we could choose if we didn't have any additional constraint for regularization or for model complexity. Now, if we introduce what is called the L0 norm, this would be the number of non-zero features. This is saying that if we constrain the number of non-zero features to be 1 instead of 2, then the solution that we can pick for our theta has to live on these axes. So if we said theta, we can't have more than one model parameter, then we have to either choose a theta 2 is non-zero while theta 1 remains 0, or we have to choose theta 1 is non-zero while theta 2 remains 0. So if we constrain to live on this surface, that is equivalent to forcing our solution to be on these unit axes. Because the shape of this region is non-convex, unfortunately solving this problem is going to be NP hard in general. So we want some relaxation of this shape that we can optimize efficiently. In fact, we want something that is as close as possible to this cross, but is also a convex shape. Now, we haven't covered convexity in this class, but convexity implies that any pair of points on the surface, if we connect a line between them, that line must also live inside of this surface. And so if I take this point here and this point here, then any point in between must also be in the green region. Clearly it is not, but we could imagine constructing a surface that looks like this, where all of these points now, so if I take a point here and a point here, all the points between those 2 points, the line connecting them, lives entirely inside of this surface. So this is a convex approximation to that cross that we drew earlier. So this is actually equivalent to saying that we want to constrain our thetas such that the sum of the absolute values is less than some parameter beta. So this is called the L1 norm ball, or the absolute norm ball. We want to find a parameterization theta that is the lowest or smallest value in the surface, so ideally as close as possible to here, but also is constrained to live inside of this diamond. By increasing the value of beta, we make this ball larger and allow the optimal regularized value of theta to get closer and closer to the original unconstrained optimization problem. As we make the ball smaller, we constrain the value of theta to be closer and closer to the origin. It is also worth noting at this point that here we're taking the sum from 1 to d of our parameters. This is a little bit of a trick in notation. Remember, if we say theta 0 is our intercept term, we're not actually constraining the theta 0 in our model. As we constrain our parameters to be closer and closer to the origin, we're essentially constraining our parameters to be closer and closer to the constant model, which is the simplest model we covered in the class so far. Now, one of the neat things about the L1 norm is that for different values of beta, for different constraints, or for different norm ball sizes, we actually have a tendency to get stuck in the corners. This is kind of a weird phenomena. Actually, if you look at the illustration here, there's sort of a glitch in my slide. Probably the optimal value of theta, the thing that has the smallest contour, is probably right here. So this red point really ought to be a little bit over here and not on the corner. But if we go down to a smaller value of beta, perhaps this one, the value that is going to minimize this contour actually is no longer on the edge, but actually would be right here at the corner of this beta 1.5 ball, right? So right here at the corner. This tendency to get stuck on corners is actually one of the useful properties of this L1 norm, is that it does actually tend to do some degree of feature selection. That is, it will often choose to exclude a subset of the features by setting their parameter values to 0. Another name for the L1 norm ball in the context of regularization is the lasso. That is not just a cool name, it's actually an acronym that stands for least absolute shrinkage and selection operator. The lasso takes the absolute value of each of the parameters, that's why absolute. It is a shrinkage operator in that it's going to move our parameters closer and closer to the origin, shrinking their values to 0. And it is a selection operator in that it will actually allow us to select a subset of our features by choosing smaller values of beta. Now, there are other forms of regularization one might consider. Another form of approximation we might consider is, instead of using the L1 norm, is to use the L2 norm. This is then taking, instead of the sum of the absolute values, we take the sum of the square values of each of our model parameters. Just as before, by varying the value of beta, we increase or decrease the size of the ball. So a larger value of beta allows our model parameters to be closer to the unconstrained model parameters, the ones that minimize the loss. And a smaller value of beta constrains our model parameters to be closer and closer to the origin. And as we move our model parameters closer to the origin, we notice that a subset of those parameters becomes closer and closer to 0. So in this case, we're moving theta 1 nearly 0 while keeping theta 2 fairly large. So we're providing another mechanism to do selection. In contrast, the L1 norm ball, as we get closer to the origin, we no longer stick to the corners. This means that some of the features, while having small weights, will not actually have 0 weights. So we discount the effect of that feature, but we don't completely eliminate it. One of the advantages of using the L2 norm over the L1 norm is that it's often a bit more robust. This is because when there are multiple features we could include, rather than selecting one of them, the L2 norm will try to balance the value across multiple potentially redundant features. In addition, because the L2 norm ball is smooth, we can actually solve for the optimization problem in closed form. In fact, there's a simple extension to the normal equations that accounts for this additional regularization term. While the L1 norm is often referred to as the lasso regularization, the L2 norm is often referred to as ridge regularization or ridge regression. And the reason for this is a little bit less obvious. So if we look at the loss surface here, we notice that it has this long elliptical structure. As we move to higher dimensions and we start to have ill-conditioned problems, it's possible to get a long strip of solutions, if you will, a ridge in this loss surface, for which any of those solutions would minimize the original squared error loss we had framed before. And so introducing this additional L2 norm ball constraint, or we'll see in a moment a penalty term in our loss, we can actually eliminate that ridge structure and make it so that there is a unique solution. So now I want to summarize what we've talked about so far. So the L0 ball we started with was sort of the ideal way to do feature selection, and this was constraining our solutions to live on the axes or a subset of the axes in our space. The L1 norm ball, or the lasso, is a convex approximation to this idealized feature selection regularization term. The lasso has the unique property that it is both convex and therefore relatively easy to optimize, and also does accomplish some degree of feature selection by trapping solutions at corners in the ball. The L2 norm ball, or ridge regularization, is a smooth approximation of the L1 norm ball. It also tends to produce models that are a bit more robust by evenly distributing parameter weights across multiple potentially redundant features. And then finally, you can combine both the L1 and L2 norm ball to get some degree of feature selection, where a few of the parameters have weights that are set all the way to 0, while also balancing redundant parameters to produce a more robust model. So these are just a few of the many ways that one can regularize models. For this class, we will just focus on the L1 and L2 norm, or the lasso and ridge regression regularizers. Now I want to return back to our optimization problem. So recall we had defined our notion of complexity as these regularization functions that we just described. And we had framed this in the context of minimizing the loss subject to a regularization constraint, where the regularization constraint is one of these regularization functions, and then beta is our regularization hyperparameter. Now this is a hyperparameter because the choice of beta, or the value of beta, is not determined by the optimization problem, but is instead determined as a design decision in the model. This is what the model developer is going to use to choose how they want to balance the fitting of the data and generalization. Now the choice of beta is going to be optimized with respect to cross-validation, which I'll talk about in a moment. But before I do that, I want to actually change slightly the way we formulate this problem. So I presented it in the context of a constrained optimization problem, but in reality, it's actually often easier to frame this as not a constrained optimization problem, but just a direct, unconstrained optimization problem, where we have a slightly different regularization hyperparameter lambda that sits in our loss. So this is the regularization hyperparameter lambda. It is related to the beta hyperparameter through the Lagrangian duality, but deriving this relationship is beyond the scope of this class. It's just a different hyperparameter which has slightly different magnitude that we'd want to choose that we'll need to optimize over. Now, why this formulation is convenient is now under this formulation, we're simply minimizing the loss plus some additional penalty for the complexity of the model. And so we can think of this as just a penalty that we're trying to minimize in conjunction with our loss. And how much we care about that penalty is determined by our regularization hyperparameter. Now, I want to give kind of a high-level picture of what the regularization hyperparameter does to the training and test error. So I've plotted here the training and test error in cartoon form. And as we increase this regularization parameter, we're putting more emphasis on penalizing overfitting at the expense of fitting our data, which means that we actually expect larger values of lambda to result in an increase in the training error. But recall, our goal is no longer just to minimize training error. Our goal is also to improve the performance on the test data set. And so we would like to choose a lambda such that we actually minimize the test error. And so I've plotted here the test error, which is again typically above the training error. And increasing the value of lambda will take a model that was initially overfitting here and then start to make it overfit less until we get to this minimum. And then it starts to underfit as we over-regularize the problem. So the value of lambda determines a bias variance trade-off, which we won't talk about today, but this will be something that we will discuss in future lectures. Now you might be looking at this plot and going, well, that's pretty straightforward then. I choose my lambda and I look at the test error and I find the lambda that minimizes the test error. But you can't do that. So you shouldn't be using the test error to determine the value of lambda. So what we really want to do is look at the cross-validation error. And so the cross-validation error I've plotted here in red. And this is a proxy, a surrogate for the test error, and is something we can compute just using our training data set. So what we'll do is, again, apply the k-fold cross-validation techniques. We'll divide our data set into a slightly smaller training set and a small validation set, and we'll do that k different ways. And each time we'll use that validation set as a proxy for our test error. And so we typically choose the value of lambda by minimizing the validation error. And then when we're done, we can look at how the resulting model for our choice of lambda performs on the test data set. Now, an important side note, as we apply these regularization techniques, it's necessary that we make sure that each of our features are in the same dimensions or the same unit space. So we're trying to predict someone's height and we're looking at their age in seconds and their weights in tons. Their age in seconds is going to be a very large feature, and so the resulting slope, the theta 1, is likely to be pretty small. Similarly, if we look at someone's weight in tons, that's likely to be a pretty small number, and so the theta 2 might actually be a bit larger. And so this vastly different scales of theta is problematic because we're treating each of the thetas symmetrically in our regularization penalty. So one simple solution to this would be one simple solution to this is to standardize our features. We want to ensure that each dimension has roughly the same scale and is centered around 0. And the way we do that is simply by computing the standardized version of that feature. So we subtract off the mean for that feature and divide by the standard deviation. Now, how do we get the mean and standard deviation? Well, we're going to need to compute those on our training data set and then reuse that for our test data set. One thing that we don't typically regularize is the intercept. So the intercept term is the extra constant that we would have in this model. So in this model here, it would be the plus a theta 0 term. And we don't typically regularize a theta 0 term because it's needed to essentially approximate the mean of the y value that we're trying to predict. All right, so these are the high-level concepts of regularization. I now want to switch back to the notebook where we'll actually walk through the process of regularized regression using scikit-learn.